All right, so remember I told you epoxides have considerable ring strain. That makes them much more reactive than other ethers. So we can also do an acid-catalyzed epoxide cleavage, but because of that ring strain, the acid does not need to be strong. Okay? So just regular aqueous acid doesn't have to be concentrated HCl or something like that. Just regular, really any old aqueous acid will open up an epoxide. And in fact, we've seen that before as a way of making trans 1,2-diols. Right? Just a little bit of aqueous acid that will protonate the epoxide, and then water will come in from behind and attack it, open it up. Water will deprotonate the H2O that added. We end up with a trans 1,2-cyclohexane diol in this case. Okay? We had made cis diols before with osmium tetroxide OSO4 because both of those got delivered to the same face. Here we do it in 2 steps by opening an epoxide, so that's why one is up and one is down. And that's similar to all the other 3-membered ring opening things that we've seen before, right? Adding bromine, if there's no water, we get 1 bromine up, 1 bromine down. If there was water present, the water would attack, just like it did up here, and we get a bromohydrin or a halohydrin, just like we had on the last page. Say you already have an epoxide. If I have an anhydrous acid, I can make a halohydrin out of that. No problem. The epoxide gets protonated first, then the halogen comes in from behind, opens it up, we get a halohydrin, just the exact reverse of the epoxide forming reaction we had on the last page. So let's talk though about the regiochemistry of acid catalyzed epoxide opening. The rules are pretty much the same as those regular ethers, we said. The less hindered carbon will be attacked by SN2 unless one of the carbons is tertiary, right? Or can in some other way stabilize a carbocation. So if I have my choice of secondary and primary, okay, look what happens here. Attack at the primary carbon is favored quite a bit. If I have tertiary and primary, we have a really good mixture. Okay, we've got 2 competing interests here. The tertiary is favored electronically because there's a pretty good partial positive charge that can be stabilized on that carbon there. Primary is more sterically accessible. So I have sterics versus electronics that are driving our product formation right here. So in this case, chlorine was added right there. In this case, chlorine is added there. So in this case here, this is the, I guess I could call that the electronic product versus the steric product, where the partial positive charge is what ruled to get the chlorine to add there, but 60 to 40 isn't that impressive of a selectivity there. So when you have 2 effects like that that are directly competing, then you're going to get a mixture of products. In this case, though, we can't get a major product because I have a tertiary and a secondary carbon. Tertiary has all the benefits of being more stable electronically. Secondary is not nearly as sterically accessible as primary. So if it's tertiary and secondary, we're gonna favor tertiary by far. So the way this works, we don't end up completely forming a carbocation like we did when we cleaved an ether with a tertiary carbon next to it. What happens is this carbon-oxygen bond here elongates just enough to form enough of a positive charge here for the nucleophile to be attracted to it. And that's important because with this CO bond still halfway formed, the oxygen blocks bromine's attack from that face. So bromine can only attack from the direction behind where the oxygen is. That's why the product here has trans stereochemistry, just like opening any epoxide like we've seen before. We get that trans stereochemistry. The bromine is attracted to the tertiary carbocation, which is more stable than the secondary carbocation that we would see if we had opened it on the other side. So this product down here is not formed because we had a tertiary carbon. We end up with the nucleophile attacking it, opening up the epoxide to the other direction. So that gives us an idea of the regiochemistry and the stereochemistry of acid-catalyzed epoxide opening, which is important for us to understand. Now, something epoxides can do that normal ethers cannot do is that epoxides are reactive to base as well. Okay? So to something that's negatively charged. Ethers cannot be attacked by something negative because we would have OR minus as a poor leaving group, right? It can be acid catalyzed because we have ROH as a leaving group, a neutral molecule leaving. Epoxides, however, they can be opened with base or something negative like that, negative nucleophiles, because that relieves ring strain. If you take a look here at hydroxide, with this epoxide right here, the hydroxide attacks the less hindered carbon. Okay? That opens up the epoxide to give us an alkoxide, to give us an O minus, which all we need is just some water to protonate that. Okay? And that will regenerate our hydroxide as a catalyst. So that's a base catalyzed epoxide opening, always to the less hindered carbon. Because the acid-catalyzed epoxide opening could open by the more hindered, more stable carbocation, that gives us some contrast here. If I have a epoxide like this one, let's do the same one we've been doing before with methyl back and the epoxide forward. I have a tertiary and a secondary carbon right there. So I can imagine two different reactions. One that's acid catalyzed, so let's just say HBr, and that's it. The other that is base catalyzed. So let's just do Br minus, for instance. So with HBr, we protonate the oxygen, and then the nucleophile attacks the more hindered carbon. So, oops, wrong color. Because there's a tertiary carbon right there that's a stable enough carbocation that it can be attacked. So bromine has to come in from behind where the epoxide is. So right there. That pushes the methyl group that was back, now pushes it forward, and then the OH there remains forward because we broke the OC bond here that's towards the tertiary carbon. Now, if I have bromide, right, just plain old Br minus, nucleophile attacking, right? I mean, that's, for instance, if we said sodium bromide, NaBr, and then to protonate the product, H2O, for instance. Br minus, a nucleophile, can just come right in there and attack the less hindered carbon. Okay? It's going to come in there, it's going to attack the secondary carbon, because there's no carbocation character here, there's no pluses or anything that would stabilize attack on the tertiary carbon. All we're going to do is attack that less hindered carbon from the opposite side as where the epoxide is. So let's put a Br down. We're going to put OH up, just like it originally was, and then the methyl down, like it originally was. Okay, so two key differences on the stereochemistry, right, and regiochemistry, right? Stereochemistry is still an anti-addition in both cases. It's the regiochemistry that's different here. Another really useful nucleophile that can open up a epoxide is a Grignard reagent. Okay? If I have butyl magnesium bromide, right? This is 1, 2, 3, 4 carbons with MgBr on it. Okay? Now it's like having this carbon right here be a C minus. Okay. That C minus will attack one of the carbons of the epoxide. Okay. That'll open it up, give us an alkoxide, give us an O minus, which we can protonate with acid as a second step. And we started with butyl Grignard. We end up with 1-hexanol because I've added 2 carbons from the epoxide to it. So if we ever need to add 2 carbons with an OH on the end, we can do so by reacting a epoxide with a Grignard reagent. So another example of that, let's do bromobenzene. It's bromo attached to benzene. And step 1, magnesium. That turns it into a Grignard, into a magnesium bromide. Okay. Step 2, ethylene oxide. There's our simplest epoxide right there. Step 3, H3L plus. Here, I'll color code this so we can follow along. What we'll end up with is phenyl, CH2, CH2, OH. 2 phenyl, 1 ethanol. Right? Something else we could imagine doing, sort of looking at it from the other perspective, is if I start with an epoxide, I guess like the one that I've been using all along here, right? Cyclohexane with epoxide and a CH3 on 1 carbon. What we can do, let's say ethyl, CH3CH2, magnesium bromide, then H3O plus. That's the second step. Here, I'll color code this for you again one more time. CH3, CH2, MgBr. Cyclohexane. Grignard reagent will attack the less hindered of the carbons. CH3, OH. And then ethyl, CH2, CH3, coming from the opposite face that the epoxide was on. Right? So be very careful, since it's a negative nucleophile, it just attacks the less hindered carbon. Okay? It always has to come from the direction opposite where the epoxide was pointing, because it's essentially an SN2 reaction. The nucleophile has to come from behind where the leaving group is leaving.